Okay, ladies and gentlemen, we're in our quadratic units and we're going to compare quadratic and exponential functions. We have been working in this unit on talking about quadratic functions, and we're going to compare that to what you learned last year about exponential functions. So first, it says, list the quantities in order from least to greatest without evaluating each expression. Be prepared to explain your reasoning. When you're finished, use a calculator to check your answer. So quantities is just a big word for number. So we have to list these numbers from smallest to greatest. Now, right off the bat, I know that 9 squared is 9 times 9, which is 81. I also know that 10 squared is 10 times 10, which is 100. Now, I don't know offhand what 2 to the 9th power is, or 2 to the 10th power, but 2 times 2 times 2, 9 times is going to be pretty big, and 2 times 2 times 2, 10 times is going to be bigger than 2 times 2 times 2 to 9 times. So if I had to put these in order from smallest to biggest, I would start with 9 squared, and then 10 squared, and then 2 to the 9th power, and finally 2 to the 10th power. In using our calculators to check this, I would go 9 to the 2nd power, and I got 81. 10 to the 2nd power is 100. To do 2 to the 9th power, you press 2 and then this caret key, 9, and it's 512. And then lastly, 2 to the 10th is 1024. So we can see from least to greatest, we are in fact correct. Moving on now, in looking at some patterns, it says in pattern A, the length and the width of the rectangle grow by one small square from each pattern to the next. So we're going to start with pattern A and look at step 0. I can see that I have 0, or at step 1, I have 0. At step 2, we have 1. At step 3, it's 2 by 2, or 2 squared, which is 4 squares. And step 4, it's 3 squared, which is 9. Now we can see the pattern growing with an exponent of 2. So I know that this pattern is going to be quadratic. Now it's tempting to just say, oh, I have 3 squared and 2 squared and 1 squared, and just assume that it's going to be growing by n squared. However, I notice at step 4, 4 squared would give me 16, and our pattern has 9. And same here, 3 squared is 9, 2 squared is 4. And what I notice, if the step number is 4, I'm taking 3 and squaring it to get 9. If the step number is 3, I notice I take 2 and square it and get 9. If the step number is 2, I take 1 and square it 9. And it looks like whatever the step number is, the side length of the square is 1 smaller. So if I look at that, if I have step 4, I would take step 4, subtract 1, and get 3, and then square it. So in general, the length is the step number minus 1 squared. So now we're going to examine pattern B. So before we do pattern B, we'll actually do and finish off the first pattern. So it says write an equation to represent the number of small squares at step n in pattern A. So in pattern A, we'll say y is the total squares and n is step number. In writing an equation, what we would say is y is equal to, if you remember back to the pattern, we took the step number and subtracted 1. And then in order to square that, we have to put that in parentheses. Because if I just put the squared over 1, it would mean 1 squared first and then subtract that from n. So I put the parentheses around that to just say we take n minus 1 to the second power. So we can see because our exponent is the second power, the first pattern A is quadratic because the variable is squared. So if I'm completing the table, if the step number is 0, 0 minus 1 is negative 1. And then I would square that. Negative 1 times negative 1 is going to equal 1. If the step number is 1, we would go 1 minus 1 squared. So 1 minus 1 is 0, and 0 times 0 is 0. And then for step 2, 2 minus 1 squared. 2 minus 1 is 1, and 1 times 1 is 1. And then here for step 3, substituting that in, 3 minus 1 is 2. 2 times 2 is 4. For step 4, we substitute in 4. So 4 minus 1 is 3. And then 3 squared is 9. Substituting in 5, we have 5 minus 1 is 4. And 4 squared, or 4 times 4, is 16. And then 6 minus 1 squared. 6 minus 1 is 5. 5 times 5 is 25. 7 minus 1 is 6. And 6 times 6 is 36. Step 8. 8 minus 1 is 7. And 7 squared is 49. So moving on now, we have to actually represent the number of squares in pattern B. So in looking at pattern B, I notice that at step 1, we have 1. At step 2, we have 2. At step 3, we have 4. And at step 4, we have 8. Now, that's an interesting pattern. And as I examine that in a table, I notice at step 1, I have 1. Step 2 is 2. Step 3 is 4. And step 4 is 8. Examining the rate of change, I see that y is being multiplied by 2. So I'm multiplying by 2, which is a completely different pattern. So here, it looks like if I continuously multiply by 2, this would be the fifth pattern, or the fifth number would be 8 times 2, which is 16. So if I'm completely multiplying by 2, let's take what we know from our 8th grade math about exponential patterns. So an exponential equation says y equals a times b to the x. Now a is our initial value, which in this case, that would be step 0. And then b is our growth or decay factor, or what we're multiplying by. Now, in this case, we can see that b is equal to 2. However, we're not given step 0. So I got to go back up here and imagine, well, what would be at step 0? So I notice to move to the right here, I multiply by 2. So reversing that process, to get step 0, I can take 1 and then divide by 2. So step 0 is going to have 1/2. Same thing here. If I started with 1 and I want to get the previous one, I could start with half of a square and then multiply by 2, and that would fit it in. So here, a is equal to 1/2. So now to write that equation with our variables, we can say y is equal to 1/2. Then I'm going to use parentheses times 2. And then instead of x, they asked us to use step n. So our variable is n. Now, because the variable is in the exponent, this is actually an exponential function. So the function is exponential because the variable is in the exponent. So if I had to figure out the number of squares here, substituting in 0, I can go 1/2 times 2 to the 0. I would use my calculator there. So a quick way to get a fraction, you can just press alpha x and then 1/2 times 2 to the 0. And we get 1/2. And then substituting in my values, instead of typing that all in, I can hit second and then entry. And just go back and change that for 1/2 times 2 to the first. And I get 1. I know that my next one, I'm going to plug in step 2. So 1/2 times 2 to the second. And then that would give us 2. And then 1/2 times 2 to the third gives us 4. In continuing that pattern, we're now going to go, and I'm just going to enter in my numbers. So second entry, I put in my 4th, I get 8. And I know that I'm just multiplying by 2. So I'm just going to take 8 times 2 and get 16. 16 times 2 is 32. 32 times 2 is 64. And then 64 times 2 is 128. You could put those in the calculator or use the calculator to multiply by 2. So lastly, what we're going to do is evaluate p of x, the function p, which takes 6 times x squared for x equals 0, 1, 5, and 10, and show our work. So essentially what I'm going to do is go 6 times 0 squared, which expands out to 6 times 0 times 0. Any number times 0 is 0. Then I'm going to substitute 1 in there. So 6 times 1 squared. 1 squared is 1. 6 times 1 is 6. And then I'm going to put in 5. So 6 times 5 squared. 5 squared I know is 25. So I can actually multiply that first and go 6 times 25. Multiplying that out gives us 150. And then lastly, if I plug in 10, 6 times 10 squared. Again, I know 10 squared is 100. So I can do that first and go 6 times 100. And then I know that 6 times 100 is 600. Now I'm going to evaluate 3 to the x if x is 0, 1, 5, and 10. So substituting 0 in, we write 3 to the 0. I know that any number to the 0 power is 1. And then I can substitute 1. 3 to the first power is 3. And then substituting 5 in, we can see 3 to the 5th power. That means 3 times 3 times 3, 5 times. I'm going to use a calculator for that. And I got 243. And then here we have 3 to the 10th. And evaluating that, we get 59,049. Now, some things that I notice. In here, on the interval from 0 to 1, P of x grows from 0 to 6. Here, on the interval from 0 to 1, we grow by 2. So it looks like if I were to say that on the interval from 0 to 1, we can say P of x grows faster to start. However, if I look on the interval from 5 to 10, P of x is at 150 and then 600. But from 5 to 10 here, P of x is at 243 and then to 59,049. So when x gets larger, Q of x, the exponential function, grows faster. Now, in graphing those, we're going to stay for positive x values. So what I'm going to do is put my two functions in. Again, I have a function in there. I'm just going to clear it out. Our first function is 6x squared. And then our second function is 3 to the x. Now, I know that this function gets very big. So I'm going to change my window. First, my x minimum, 0. And then I'm just going to go to the first 10 steps. The y minimum, again, for our range, we have only values defined by 0. And then we know that we have to go up to 60,000. And then adjusting our y scale, I'm going to count by 5,000. And then see what our graph looks like. So we can see that our quadratic graph is lower, but our exponential graph grows faster. And we're going to examine that same thing. So if we did a much smaller one, we would see this and then this on a larger scale. If I did a smaller window and just did the standard window, we can see the quadratic function and then the exponential function as well. So on a smaller window, depending on how you view this, you might have your parabola and then your exponential.